Yeah,
Physics
so
like Troy spells it.
No, it's not true at all.
if we have a nearly equilateral triangle, and these are all identical point masses, guys, shh. This one will have a force on it like so, this one will have a force on it like so, and that will be the same for each of the vertices here. And since they're equally spread, all of those forces would be the same. So, and of course, as we've pointed out before, these would be equal magnitudes, but obviously not equal forces, because they wouldn't be in the same direction. But that's not what the question was. It was just the magnitude. Number 12, object A weighs twice as much as object B when at the same spot on Earth. Would the same be true at a given spot on Mars? Would A weigh twice as much as B if they were both on Mars?
Yes, because weight is a measure of force. Force is mass times acceleration. They both have the same acceleration, so their mass must be once twice.
So the long way to write the gravitational force is capital G times the mass of the planet you're on times your mass over the square of the radius, so that'd be the radius of the planet. These parts would change if you went to Mars. Note the mass of the planet and the radius of the planet, but they'd still be the same for the two objects. The only thing that's different is the mass, so if one has twice the mass of the other, one will still experience twice the force, even though both would be smaller forces on the planet, or on Mars, than they were on Earth. And if at any point you would want to interrupt me with, wait a minute, don't go on to the next question, please do so.
Wouldn't G be the same?
G is always the same everywhere. Yeah. So the mass of Mars is different than the mass of Earth. The radius of Mars is different than the radius of Earth. So this number would change, but it would change the exact same way for both masses. So on a scale, like I say, you'd weigh less if you were on Mars, but you'd still weigh twice as much as something that you weigh twice as much of as on Earth. And 13, does the acceleration of a freely falling object depend to any extent on the location? That is, whether the object is on top of Mount Everest or in Death Valley, California. Troy?
No, because you can assume all the holes on the planet can come to a single point in the middle.
That is mostly true.
It would change, but from Mount Everest to Death Valley be so small that it's not really considerable. But where if you're like satellites and stuff, that's gonna be way different. But like just a little bit of difference between Death Valley and Mount Everest, that's not gonna be big enough.
It's not going to be big. That's true. What do you have to add?
Because the further that you get away from the Earth's core, the weaker the force of gravity acts on you.
Yep.
That's why if you go way out in space and there's nothing around you, you still will be pulled, just not nearly the same.
Okay, so similar to what he was saying. So yeah, essentially those are true, although if we consider Earth with Mount Everest and Death Valley, exaggerated slightly.
No, it's exactly the size.
And then we measure to the center of this planet. Now technically speaking, of course, we have to do if we really want a close measurement, we have to do the measurement from you, all of your points to all of the points, and we'd use calculus to sum them up with an integral. But remember what we talked about too, that if you're down here in Death Valley, what is actually affecting you, assuming everything else is uniform around you, is whatever is inside. So we would have smaller acceleration because there's less mass between you and the center of the Earth. It is very small, but it is measurable amounts. But that might change the acceleration of gravity from maybe it's 9.78 meters per second squared on top of Everest to, I don't know, 9.82 meters per second squared within Death Valley. So measurable, but for our purposes, probably not significant. Interestingly, though, we can use this, and for those of you who were in last year's, we talked a little bit about this. we can actually use this slight differences of whatever is underneath and pulling most strongly on something for some underground exploration using fancy clocks.
No.
Because gravity, mass, distorts space-time. That's what one of Einstein's findings was. And when that space-time is distorted, clocks run differently. So slower the closer they are to mass. And we have accurate enough clocks and precise enough clocks now to put one up here. And based on what is underneath it, we can measure those slight variations of gravity that indicate different densities down there and say, oh, this is bedrock, 20 feet down, or hey, there's something fairly low density. That might be oil or natural gas under there, based on what that clock is reading, some of our atomic clocks. Okay? But we couldn't measure that with our experiments for sure. Questions on any of the problems from chapter 4? Yep. 26. 26 asks, a space traveler weighs 540 newtons on Earth. What will the traveler weigh on another planet whose radius is 3 times that of Earth and whose mass is twice that of Earth? So the first thing I do is find that person's mass on this. And I would do that, we could do it more precisely using the big equation. So we'd use mass of Earth times the mass of the person over radius of the Earth squared. Actually, we won't need to do that. We won't need to find the mass. So that's force on Earth. We want to find out what is the force on the new planet, planet 9. Okay, and we know some related values to this. We know G is always going to be the same. The mass of this planet is twice Earth. So I'm just going to put in twice this. 2 times the mass of the Earth. I didn't figure out what our mass is, but it's not going to change. And then we have the radius of this planet is 3 times Earth radius. So all we really have to do is compare it back to Earth's force, because we know that this is 540 newtons. So if I bring these numbers out, I've got a 2 on top, and then 3 squared is going to be a 9. But then the rest of this, what's left, is G times the mass of the Earth times our mass over the radius of the Earth squared, and I already know this is 540 newtons. So my new weight on that planet would be 2/9 of my weight on Earth. So the quicker way to do that. You could also, as I said, back it out, find your mass, and then go put in the actual values, but that's really a long way to do it. Which is 120 newtons. Yep. Other questions on problem set 4? That's, by the way, this is not always an obvious way to do it, particularly when you are starting out, but it sure is a time saver. If you can realize, oh wait, I'm just multiplying this by 2 and this by 3. Compare. Other questions on chapter 4? Okay, let's look at chapter 5 questions then. The speedometer of your car shows that you are traveling at a constant speed of 35 meters per second. Is it possible that your car is accelerating?
Yeah, you can change direction.
Could be changing direction. Yep. And many times our roads aren't quite flat. They go with the curvature of the Earth, so there'd be a tiny bit of acceleration there anyway. But yeah, if you're going around a corner, you're accelerating even if you're at a constant speed because you're changing direction. And acceleration is a vector. It's the vector change of velocity over time. So we'd have to figure that out. Centripetal type.
The curvature of the Earth, I thought it was flat.
Indeed. Who are you who is so wise in the ways of science? Consider two people, one on Earth's surface at the equator and then the other at the North Pole. Which has a larger centripetal acceleration? Okay, person at the North Pole, person at the equator, who has the greater centripetal acceleration, or are they the same? We can assume the Earth is a perfect sphere for this. No.
The person at the equator,
How come?
because when it's spinning, it has a bigger loop.
Yeah. Because all indications show that the Earth is, in fact, mostly spherical. And so if we're trying to find a centripetal acceleration, that's going to be the linear velocity squared over the radius of the motion. So the radius is quite a bit larger here, of course, but it's actually spinning. And the person up here isn't really spinning. They're not, they're going through space with the planet, but they're not really spinning around it. So this would be a lot higher because there is some. We're not tumbling this way as well. Number 3. The person on the equator, because they're actually going around in a big circle. So they'd have quite a lot of centripetal acceleration based on that. Number 3. The equations of kinematics, so those are the ones we call Galileo's equations, describe the motion of an object that has a constant acceleration. These equations cannot be applied to uniform circular motion. Why? Cody?
Yeah. The direction's constantly changing, so
Mhm.
velocity is not changing, but still accelerating.
Right. So if we take this away and consider it as a spinning disk, what direction is the acceleration here? What's that?
And you'll flat disk.
What is the acceleration on that point in the disk if this thing is
Tangential to the,
not tangential? The acceleration
Center.
towards the center. Acceleration is in towards the center. What about down here? In towards the center. So, as Cody said, the acceleration is constantly changing because it's changing direction, so we can't use that anymore. If we did more work on circular motion, we would get very similar equations to what we had seen previously, but instead of being an equation like this, we would have to use circular motion. So instead of x, what changes on a rotation is theta, an angle. We'd have rotational equivalents of these, which we abbreviate with an omega. T time is the same, and acceleration becomes circular or rotational acceleration, and that's by an alpha. We get the same equations. These would just involve circular motion rather than linear motion like this. But the acceleration is different. It is. Yep. Yeah. If you followed the reading, then you saw how to get some of those at least. 4. Is it possible for an object to have an acceleration when the velocity of the object is constant? I think we kind of already answered that one. When can you have... What's that? In an orbiting object. Or anything that's actually changing its direction at the time. When the speed of the object is constant, same deal. And in each case, give your reasoning. So, same deal. The acceleration can point in a direction not there. 11. A penny is placed on a rotating turntable. Where on the turntable does the penny require the largest centripetal force to remain in place? On the edges. Why?
Because that would be the hard disc that would be moving the fastest in comparison to the rest of the
Right.
whatchamacallit.
Has the most acceleration, how fast?
It has the most acceleration because the centripetal acceleration is v squared over r. So the as r gets bigger, this v actually changes more quickly than the r, so you multiply that by itself and it's going to need more. Yep. And we know this almost instinctively based on, if you've been on one of the playground merry-go-rounds that you can really get going faster. We used to hang onto the edges and then let ourselves go out, and it was a lot harder to hold on than if we were in close. And then we would throw up. Questions on the problem set? Chapter 5, we good there?
Nope, I know it.
Wunderbar. Okay.
But why do you feel like throwing up when you're on a merry-go-round?
It has to do with how your